Assalamualaikum and hi, my name is Najwa Binti Azzahari. My supervisor is Dr. Husni Hani Jameela Binti Sapingi. My title for final year project is Determination of Adulteration Trace in Edible Oil by using Optical Fiber Sensor. Edible oil is one of the essential needs in daily life. It contains good nutrition that can lower the risk of health issues and provide many benefits. Consumption of healthy natural dietary fats are recommended in enhancing the nutrition needed in our body according to the food pyramid suggested by the Healthy Eating Pyramid. Consumption of unsaturated fats in proper proportion can minimize the intake of consumption of trans fat and saturated fat that can affect our health. However, edible oils tend to be adulterated with additional substance that benefits the manufacturer due to its rich composition of nutrition, and some of the edible oil can be quite expensive. The addition of cheaper substance and animal-based fat will affect the quality of the oil and will result in some human health issues such as allergy and health problems. Shift single mode optic fiber sensor has become one of the methods in determining the refractive index of the adulterant added in any light medium. The qualities possessed by the optic fiber sensor, including permits the ability in evaluate the light attenuation throughout the core and cladding of the fiber. The determination of adulteration trace in edible oil can be conducted by evaluating the electric field distribution and the refractive index using COMSOL multiphysics software. Problem statement for the research is when growing concern over the adulteration of edible oil contributed into a confusion on the authentication of edible oil. The adulteration of edible oil may lead to the health issue to the consumer. Detection of adulteration in the edible oil can be determined through the optic fiber sensor. Simulation will be conducted on determining the adulteration of edible oil through the COMSOL multiphysics software. From there, we will evaluate the optic fiber sensor whether it is capable to detect the adulteration in oil. The objective for this research is first, to stimulate an optic fiber sensor to detect adulteration trace in edible oil. Second, to evaluate electric distribution and refractive index using COMSOL multiphysics. And lastly, to identify the best optic fiber sensor for determining adulteration trace in edible oil. This research focused on determining the adulteration trace in edible oil by simulation work along 2 semesters. This research aimed to determine the refractive index material and evaluation of electric field distribution within the core of D-shaped optic fiber sensor using COMSOL multiphysics software. Based on this research findings and structure design of the D-shaped optic fiber sensor on the COMSOL multiphysics software, the objective of this paper can be achieved. Methodology of the research. Structure of single-mode fiber consists of core and cladding, where it is used to transmit a long-distance signal transmission. The optic fiber sensor is designed using COMSOL multiphysics software by placing 2 circles of shape overlapping with different radius. The radius of circle is 4 micrometer and 62.5 micrometer of core and cladding respectively. This illustration is the design 2-dimensional of optic fiber sensor using COMSOL multiphysics software. D-shaped optic fiber sensor designed to be removed partially at the cladding area above the core of the optic fiber sensor. The removing part on the optic fiber sensor is demonstrated to enhance the sensor's sensitivity and ensure the surrounding of analyte medium to be synergy to produce evanescent field. In experimental setup, D-shaped optic fiber sensor will be demonstrated through the side polished surface above the core of the fiber, where it will expose the analyte medium with the fiber core. The illustration shows the structure of two-dimensional and three-dimensional of D-shaped single-mode optic fiber sensor using COMSOL multiphysics software. In the simulation, rectangle shape with the width and height of 160 micrometer and 40 micrometer respectively will be placed overlapping on the half of the cladding structure on the single mode fiber constructed. The exposed area will be surrounded with the analyte medium, which is adjusted with different refractive index value to evaluate the electric field distribution at the core of the fiber. The illustration shows the overlapping rectangle shape on the single mode fiber. Scattering boundary condition under electromagnetic wave and frequency domain in COMSOL multiphysics has been applied in designing the single mode fiber because it is used to prevent back reflection projectile from outgoing wave due to the exterior boundary of domain. The scattering boundary condition works by underlining the outer layer of the single mode fiber with a bold line. That condition designed to shift the incident light wave from the boundary of the fiber. These results explain about the outcome of this research. It will explain briefly through the data collected from different refractive index of the analyte medium. The data collected can be shown through the significant changes of the refractive index and the variation of electric field distribution within the core. The higher order modes penetrate the cladding layer as the refractive index of the analyte increase. This causes the drop of output intensity of the edible oil. The data collected is conducted through the simulation of COMSOL multiphysics with different range of refractive index from 1.40 to 1.50. The color intensity of red to blue indicates the maximum and minimum electric field intensity. Illustration shows the intensity of electric field distribution of D-shaped optic fiber sensor when approaching the analyte medium at 1.40 of refractive index. It shows that light concentrated at the fiber core and equally distributed in the fiber optic. Furthermore, the second illustration shows the intensity of electric field distribution when approaching analyte medium of 1.45 of refractive index. The illustration shows the light attenuated shifting from the fiber core into the analyte medium. As the refractive index of the analyte medium increases, the chance for the light to probing further into the analyte is also higher. However, starting when the core of the D-shaped optic fiber sensor exposed to analyte medium with refractive index of 1.49, the light intensity in the fiber core is completely lost into the analyte as shown in the illustration. This is due to the high refractive index of the analyte medium, which promote the complete light attenuation into the analyte medium. Mode field diameter will be observed to study the transition of the electric field distribution according to the change of refractive index in the analyte medium. Mode field diameter depicts the intensity of mode field distribution from the core of the fiber. As the light propagating in the optic fiber sensor core, the extended light will cause fraction of radiation at short distance in the medium of lower refractive index. The illustration shows the variation of mode field diameter of the D-shaped optic fiber sensor correspond to the change of refractive index of the analyte medium. The increase of refractive index in the analyte medium increase the penetration depth of the evanescent wave. As it's shown in the illustration, when the analyte medium at 1.45 yellow line at the trend line of the mode field diameter starting to propping further to analyte as it leads to more energy distribution to the analyte. This condition causes the optic fiber sensor to face decrement of electric field intensity at the core fiber. This mode field diameter is simulated using COMSOL multiphysics software. Confusion on the authentication of edible oil occurs due to adulteration in additional substance. It can be overcome by a proper method and well-developed sensor that helps to detect adulteration trace. The objective of this research are achieved as the simulation on the optic fiber sensor capable to detect changes in refractive index. Furthermore, it is proof that it can evaluate the electric field distribution and refractive index, where the data collected shows light attenuation at the fiber core. It is proven that D-shaped single-mode optic fiber sensor capable to detect adulteration. In future work, adulteration in edible oil can be determined through the proper parameter and capable to prevent oil fraud. The simulation result shows using the COMSOL multiphysics compared with the measurement results. That's all from me. Thank you for watching my video.